Hello, Mr. Harry, Mr. Ryan, are you right?
Yeah.
Okay, so what did we talk about last lesson?
About lucky numbers.
Lucky number, okay. Okay, so last lesson we talked about lucky numbers and we talk about this recursion, right? Basically, we can find out this. Given this table, right? The first solution to find the kth lucky number is to do this mapping to the binary. And we also find out that we have this recursion. Fn equals, in the base case, if n equals 1, n equals 2, we know the answer immediately. Otherwise, it equals to n minus 1 divided by 2. If it's an odd number, it's based on f n minus 1 divided by 2 plus 7. Otherwise, if it's an even number, it's plus 8. Okay, this is the recursion. As we can see, Fn depends on half of it. So the term complexity is log k. And this corresponds to, this also matches the first solution, which is using the binary. I'm going to draw a data structure and you tell me what it is, okay? 7, 8, 7, 7, 7, 8, 8, 7, 8, 8. Okay, and this could be 0, okay? 7, 7, 7, 7, 7, 8, 7, 8, 7, 7, 8, 8, 8, 7, 7, 8, 7, 8, 8, 8, 7, 8, 8, 8. Okay, so what do we have?
Tree.
A tree, yes.
A binary tree.
A binary tree, a binary tree. Okay, so it's tree, it's a binary tree.
An upside down tree.
Tree is upside down in computer science. So this is the data structure binary tree. So these are 5 different types of trees. This one, every node has 0 or 2 kids, right? 0 or 2 kids. We call it full binary tree. This one, every level is complete except the last one, right? Except the last level, and all the nodes should be as left as possible. We call it complete. Every levels are complete except the last one, and the nodes should be as left as possible. This one, all the internal nodes has 2 kids. The leaf node should be at the same level. This is called perfect. The height of the binary tree is h. The total number of nodes is 2 to the power of h minus 1, right? For example, the level is 1, 2, 3. 2 to the power of 3 minus 1 is 7. 7 nodes. 1, 2, 3, 4, 5, 6, 7. 7 nodes, okay? Perfect. This one, most of the nodes has 1 node instead of 2. So this is called degenerated binary tree, a linked list. And this one, the difference of the height for the left kid or right kid is no more than 1, and we call it balanced binary tree. Okay, it's quite balanced. Okay, we want to find out the kth lucky number. Left kid is 7, the right kid is 8. Now in this way we can construct the kth lucky number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Do you see this? By performing which order we get the sequence of the lucky number. This is infinite binary tree, right? This goes on. It's infinity going, and we can say it's a complete binary tree, okay? It's a complete infinite binary tree. Performing which order gives the sequence of the lucky number?
Breakfast search.
Breakfast search, you look at 7, 8. So that gives us one solution to solve it, yeah? But the thing is that this tree could be very large. If k equals a million. And one way is to construct this complete binary tree with a million nodes. And then we just perform the breadth search. And breadth search consumes the space as well. It's not very optimal, but we don't need to actually construct this binary tree. Think about how do we get this kth lucky number. For example, k equals 1, 2, 3, 4, 5. K equals 5. How do you know this is 87, given this tree?
You can just count.
How do you count? Yeah, that's the thing.
Search.
Yeah, but k could be very large, and you need to construct this binary tree. We don't have this binary tree, and in order to construct this binary tree, it could be very time and space consuming, right? Make sense?
You can just do the first 3 levels and then 1, 2, 3, 4, 5.
Count. Okay. Think of the opposite way. Let me do it. Look. This is k equals 0. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So the left kid, can you tell me how do you get the left kid from its parent? let's just look at this. 7 is equals to 2 times 3 plus 1, right? 3 is equals 2 times 1 plus 1, right? Look at this one. 11 is 2 times 5 plus 1. 13 is 2 times 6 plus 1, am I right? And the right kid is 2 times the parent plus 2, am I right? For example, like this one. 12 equals 2 times 5 plus 2. 14 equals 2 times 6 plus 2, am I right? Okay, so the parent, the left kid equals parent times 2 plus 1. The right kid equals parent times 2 plus 2, am I right? Okay, why is this useful? This is very useful. It's not easy to go from top to the bottom, right? To count. We don't want to count because that's very slow. But we can do the opposite. We can travel from k. For example, we want to find out the fifth lucky number. We can travel from here to the root.
But you have to make between in the first place.
No, I don't need to make. This is the beauty. Look, we want to find out the fifth lucky number. 5. The odd number is the left tree. Am I right? The left tree is odd number. The right tree is the even number. So 5 is the left tree, right? Left tree. So we should add 7 here. Do you know how to go from here to here? We know how to get from here to here. If it's a left tree, if it's an odd number, then we can minus 1 divided by 2. So 5 minus 1 equals 4. 4 divided by 2 is 2. Here, right? We go here. And now, right, this is even number. This is on the right tree. So we should add 8 here. And then we go back to the root and then we're done. But this is 78. So what do we need to do? Reverse, yeah, because we're traveling this way, right? Then we need to do this. Okay, let's find another example, this one. 778, okay? And the 8th lucky number. The 8th lucky number. It's on the right hand side. It's on the right hand side, so we should add 8. Then we travel back to its parent. 8 minus 2, because it's on the right hand side, it should be minus 2 divided by 2. So here, right? Now, this is on the left hand side because it's an odd number, right? It's an odd number. So we should add 7. And then we go back here. Now it's on the left hand side, it's 7, right? Let's add 7 and go back to the root. And once we are root done. 877. This is not the answer. We need to reverse it. 778. Why? Because we are traveling from the k back to the root. Then we need to reverse it. Does it make sense? Okay, so the beauty of this approach is that we find out in the complete or perfect. Every perfect binary tree is a complete binary tree, okay? Every complete binary tree or perfect binary tree. The left kid, if the root is index 0, the left is multiply 2 plus 1, the right is multiply 2 plus 2. And we also can go from the left to the parent, which is minus 1. Left minus 1 divided by 2 equals the parent, or the right minus 2 divided by 2 equals parent, right? And then we travel from the kth node back to the root node. Okay, so this way we don't need to actually construct this binary tree, right? We are not counting from 0 to k. 8th lucky number, how do you know this is the path? We need to go backward, right? Otherwise, if we have this binary tree imagine the binary tree, and we can do this level by level, which is effortless, but it's very slow because you're counting. You need to count. You need to traveling this. This is okay, right? Okay, but we are traveling this way, from the k. Every time we go one level up to the parent, to its parent, to the parent, this is O log k. Make sense? This way is better, and we don't actually need to construct the binary tree. Okay, let's write the code, okay? Define f k. We'll put this in an array. While k, we haven't arrived the root node, right? Then if k and 1, if it's an odd number, if it's the left tree, then we need to add append. The left is 7, right? 7. And then k equals k minus 1 divided by 2. Else, if it's an odd number, if it's on the right hand side, then append 8, right? And then k equals k minus 2 divided by 2. And return, we need to reverse it, right? Colon minus 1, and then dot join. The time complexity, as I said, O log k. The space complexity is also O log k, okay? or locate.
Yeah.
Okay, so what have you learned today? And that's it. We have talked about 3 approaches, including this one. So which one do you think is the best? This one here?
This one.
Yeah,
Why
it's
would
very
you do it
elegant,
long?
yeah? Very amazing, yeah?
Number one, you already said it's very brilliant and beautiful, simple. And secondly, why would you pick this as the last one?
No, this is not last. I can keep talking for a few lessons. There are a few other solutions as well, okay?
So we've been given, the problem is we've been given a cave number
Mm-hmm.
and we have to find a cave lucky number. For this one, if a k is an odd number, then we know it's on the left side, and if it's an even number, it's on the right side. If it's on the left side, we subtract 1 and then divide by 2, since we're doing it from bottom to top instead of top to bottom. And if it's on the right side, then it subtract 2 and then divide by 2. And then if it's an odd number, you just put 7, and if it's an even, you put 8. And then when you get to the root, then at the end you reverse it, and then you get, yeah.
Well done. Okay, that's it for today. Bye-bye.
Bye.
Bye.